Hello and welcome to our webinar on discovering complex causal structures with Hellixia, BayesiaLab's new subject matter assistant. My name is Stefan Conradi, and I'm the managing partner of Bayesian USA and Bayesian Singapore. I'm delighted that so many of you have joined us today. Today's event may actually turn out to be our most popular webinar ever. As of this morning, we had nearly 400 registrations. Now, I'd like to extend a special welcome to my friend and colleague, Dr. Lionel Jouve, who is joining us from Bayesia's headquarters in France. Lionel is the CEO of Bayesian, and Hellixia is his brainchild. So there is no one who would be better qualified to tell us about Hellixia's capabilities. Before we start, however, let me just mention that you have a Q&A panel where you can submit questions. However, given the large number of participants and our limited time, we will not answer your questions live. Rather, we will collect the questions, compile them, and then share the answers with everybody after the webinar. Now, it's time for me to hand over the meeting controls to Lionel. The stage is yours.
Thank you, Stefan, for the introduction, and welcome everybody. Indeed, lots of people today. I hope you hear me okay. Stefan?
Yes, we do.
Okay, perfect. Let me share my screen. Okay, so today's webinar is about using Hellixia for discovering or creating automatically causal structures, right? And so I want just to start with what we are going to see in a few minutes. So this is one of the results. So one network that have been created with the new feature of Hellixia. So it's a causal network that I'm used to say that it's now a fully specified causal Bayesian network. So we have not only the nodes, but we have also the links with the causal effect, and also the conditional probability tables that are populated, right? So at the very end of the creation of this network, you can switch to validation and play with this network. Obviously, Hellixia is just a subject matter assistant, so you always have to check if it's correct or not. But it's already a good start because you really have something to play with. And so the topic I've chosen today is the delay in scheduled flight departure. So even though now we are flying less than we were doing before COVID, but still this is something that is still interesting, right? So this is what I'm going to show you in a few minutes. First, I want to just go through the different features of Hellixia I'm going to use today. I'm going to use the dimension elicitor. So now I think people are quite used to this feature. So this is the feature that allows us to create automatically nodes of interest. I'm going to use also the embedding generators, because first, before creating causal Bayesian networks, I will, as usual, create semantic network just to have a broad view of the domain, right? Then after that, I'm also going to use generate descriptions. So this is for defining useful names for describing our automatically generated factors when we do the PSEM, the probabilistic structural equation models. And then I'm going to use the causal network generator. I'm going to use the image generator for creating icons. I'm going to also use the pairwise causal link, so the name that's changed since December. And the new feature, also the causal relationship finders, right? So these are the features I'm going to use, and I'm also going to conclude with the Hellixia report analyzer. So we're going to have two main parts in this webinar. So the first one, during 15, 20 minutes, I don't know exactly, is going to be about using Hellixia for creating semantic networks and hierarchical semantic networks, just to really understand what are the dimensions of this domain of flight delays, right? And then after that, I'm going to directly switch to the causal analysis of flight delays by creating a very first simple Bayesian network, causal Bayesian network with a causal network generator, Then I'm going to go through a much more complex network. And after that, I'm going to illustrate the utilization of the causal relationships finder. So it's more or less the same thing as a causal network generator, but using here a set of predefined nodes, right? Just a few words about the models we can use in BayesiaLab. So Hellixia can use, obviously, all the OpenAI completion models, but we can also use Azure. We have a way to connect endpoints. And since we have these endpoints, we can also use some kind of private endpoints. For example, here in my screenshot, you can see that I'm also using Mistral. So it's a way to test different engine if you want. So you just have to go through the preferences and then define your endpoints here with the name, URL, the key of the API. Same thing for now the assistant. So they have been released a few weeks ago. So these are the GPT assistants that you are designing by yourself. So mainly here, it's when you want to include some specific documentations that are going to be used as context. So it can be very useful. So I have here a few examples with, for example, the skin sensitization potential, the wildfire, and so on. So you can then include them in the available completion models that can be used by Hellixia, right? So first, the semantic networks to get a very broad view of the flight delays. So this is what we are going to have in a few minutes. So this one is a simple semantic networks that is focusing on the causes of delays. And this one is a hierarchical semantic network. So this is a hierarchical version of this semantic network. So when I say hierarchical, this means that we have manifest variable and we have also latent variable factors that have been automatically created. So this is now what I'm going to show, how we can build these networks. So first, at the end of the webinar, right now we are uploading version 11.2. So it should be available tonight, at least in Europe. And so you are going to be able to find all these features in this new version, right? Then I want just to also focus a little bit on the media center. So I'm not sure you are using it a lot, but you see there is this new icon here that show you that there are some new content. So in this media center, you have PDF and videos. So the PDF, so since a few weeks, we are, for those who have a commercial version of BayesiaLab, so the 1-year license, you can have automatically included the introductory course and the advanced course. So you have all the material available in the media center. So you have the PDF and then also the videos that correspond to these trainings. And you have also all the recorded webinars that are there. So for example, here you have the webinars that we gave last December about Hellixia, right? So if you click on this, you are going to have access to the video. So you can obviously increase the size, go to full screen, and then play the video just to learn, if you will, right? So this was just to remind you this feature. And then, so now let's switch to the topic of the day, delay in scheduled flight departure, right? So as usual, we first need to create a node. So I'm creating the node delayed in scheduled flight departure. Then I'm selecting it and I'm going to start to learn a semantic network with that. So I first go to Hellixia and use the dimension elicitor. So you see now we have more and more options since we created this feature in February, but we add every week we are adding things. So here you first have the list of keywords. Now we have 155 keywords. So these are the keywords you can use to get a sense of the domain if you want. So we have these keywords, and we have on the right, you have the group of keywords. So this allows you to create groups of, a group of keywords that you are using frequently. So for example, here I've created 3 groups for this webinar. I'm just going to use 2. The first one is ancestor. So this will allow me to capture what are the dimensions that can be at the origin of the flight delay. So I have accelerators, barrier, booster, catalyzer, boost, drivers, and so on and so forth. So not only the causes, but also the things that can mitigate flight delays. And I have also the descendant. So the descendant where I have accomplishment, aim, consequences, cons, deliverables, and so on. So you have these two set of keywords that we are going to use for having an idea of this domain. And the descriptor, I'm not going to use them today. So I'm selecting these two groups. So at the end of the day, I'm going to use 28 keywords, right? And I'm not limiting the number of responses per keyword. I'm going to exclude the duplicates. And here I can choose the completion level I want here. So you see all the list of the one I showed you a few minutes ago. But I'm always using GPT-4 Turbo because it's also the more expensive one, and this is really the most powerful one. Then here you can associate a knowledge file, even though this feature now, given that we can use a GPT assistant, is less useful than it was. So you can, if you really have a context, you just use your GPT assistant. You can also define a general context. So here I define the applied operation coordination. And then you select what are going to be the main subject of the query. So here I just have a name, a node with a single name. So I just select node name. And this is a new set of settings, if you will. So when you see the cloud in red, this means that this is a new feature. So now you can choose the language. So you have access to lots of different languages. So English, French, Spanish, and so on. You can then also define what or not, because this is, if you don't check this box, so you are going to let GPT-4 here choose what is the optimal length. But here you can also influence the result by defining a description length between short and long. So this will create names that are longer or shorter, and also the comment associated with these nodes, right? So here I'm just in between short and medium. And you can also create classes. So what is new here is not just to create class per keyword, but we can also now create a class per keyword group. So here I'm going to have a class for the ancestor and a class for the descendant. And here it's in big because it's a trap. Yes, it's not easy to see this button submit query, but you have to hit it and not just directly go to OK, because if you click on OK, there is no result. So the OK is really for validating the nodes you have discovered, right? So first you hit query, and then this is, obviously here it's a little bit accelerated, and we are finding the nodes here. So you see we have 111 nodes that have been created. We have excluded duplicate because we have lots of time weather condition in this case. And then, so once we click on OK, this will trigger the creation of these 111 nodes with their associated comments. So I'm going to generate embeddings for all these nodes, but first thing, I'm excluding the node delay because it does not matter anymore. I have all the dimension I want. And then I'm selecting all these nodes and go to Hellixia embedding generate, right? I can select here what I'm going to use for creating these embeddings. So I can either use a node name or the node name, the long node name with the outcome, goals, and so on, what's between bracket here, or M, because we can use the three at the same time if we want. We can also include the node comment. So here I'm going to use a node name plus the comment that is associated with the name, right? So this way I'm going to have nice embeddings, right? So as you can see now, we have a data set made of 1,536 rows. So for those who did not see the previous webinar on that and who are not familiar with this embedding, real quick what it is, it's this vector of 1,536 dimension is indeed the weight associated with the neurons here. So you have 3 layers. So it's a basic neural network with 3 layers. So the first layer is you have 1 neuron per token. The last layer is 1 neuron per token too. And the idea is to predict when we see 1 token, what are, among all the documents we have seen, what are the tokens that we can find before and after this token, right? So they have learned by using billions of documents, they have learned this very simple Bayesian network with only one hidden layer. And then, so the hidden layer at the end of the day is made of 1,536 latent variables that represent some kind of concept of semantic concept. And then we, instead of using just an ID for the token on the left, we are using this vector of weight. So this allows to have a very powerful, very rich description of the token, right? So this is what we use now for having a data set associated with our network. So as you can see now, the nodes are dashed with dash borders. So this means they are continuous, because these embeddings obviously are weights that are more or less between -1 and +1. And we have discretized them by using equal frequency with 5 states, right? So now that we have this data, we can machine learn and learn a semantic network, right? But first thing, I had defined ancestor and descendant here because I want to create 2 networks at the same time, right? And I don't want to mix ancestor with the descendant. I'm going to create a constraint here where, so I go to forbidden arcs, and I'm just going to say that I don't want to have any connection between ancestor and descendant, right? So I just want to have intra-class connection, if you will, right? So I'm defining this constraint and then go to the maximum weight spanning tree and learn my semantic network, right? So now I'm using my basic layout algorithms, my 2 steps, so first radial and then semantic, just to be sure that I'm not going to have any crossing edges, right? And now I'm going to move this network from the right. And if I just go to the classes here, I can just uncheck all or check here to see, so that on the left, I have indeed the networks that correspond to the ancestor, and in the right, the descendant, right? Now we're going to see a little bit what we have learned. So I'm switching to validation, go to node force analysis, and we are going to have the mapping that is very useful for analyzing the network, right? So we have this mapping, and we can go through the different dimensions that have been generated here. So we see that weather is important. So weather has impact on delay. We have also flight planning. We have fueling. So we have also the late arriving aircraft. We have some medical emergency, security problems, boarding delays. We have also problem with obviously the baggages, the cargo. And so you can see all these dimensions that are, so you see maintenance, contingency planning. So these bird strike here, these are the dimensions that have a relationship with the flight delay, and that are the ancestor of flight delay, right? So this gives you a broad view of what we can find in this domain. And now if I go to the descendants, we can see that this delays allows to solve technical issues, but then you have to take care of the customers, and you have obviously dissatisfaction. So you have to notify the passengers, you have legal repercussion, and so on and so forth, cargo delays. So this allows better weather assessment, will allow to reduce the risk. You have the time for doing maintenance, which is usually the reason why you are delaying the flight too, and so on and so forth, right? But you have also this negative brand reputation and so on, right? So this allows us to have a view of this domain. So we can spend a lot of time analyzing this network. So we have 69 nodes, I think, in this dimension. And then, so now that we have this network, we are gonna just go through variable clustering. So this is our usual step for what we call the probabilistic structural equation model, the PSEM. So we first use variable clustering, so which means that we are going to analyze the strength of the relationship between the manifest variable. and then use a hierarchical clustering approach for creating classes of nodes, right? And so this allows us to have this view. So it's a hierarchical view of the exact same network I just showed you, right? But with latent variables. So the name that you see here is the name of the strongest node belonging to the factor. So we are working on a version that will allow us also to use Hellixia to name the nodes here, but it's not ready. And then, so now that I have my factors, I'm gonna create the nodes, because here it's a purely qualitative right now. So I have defined classes of node, but I need to create a latent variable. So to create nodes for each factor. But first thing, I'm going to use Hellixia now for creating a node, because a name of the node, because as you can see, choosing the strongest node it's convenient because we are not losing any information, but it's not the best solution. So here we are going to use Hellixia for analyzing what are the nodes that are grouped together, and then create a node that summarize this set of nodes. So same thing, you can choose your completion model, you choose a subject of query. So I'm just using here the node name, the language, and the description length. So here, short name, right? So this is quite quick here. And we have this description for all the factors based on the nodes that have been associated, right? I'm exporting this name in a file. So this will allow me to rename in my hierarchical network, to rename the latent variables, right? And then last step, I go to multiple clustering. So this will allow me to create the very classical workflow now. Just choose the usual option. And then we create one hidden node per class. And we have this final network with all the nodes. The latent variables are connected with their manifolds. I'm going to use radial layout and see a field. I'm used to call that the field of flowers. So you have all the manifest variables that are connected with their latent variable. And what I want to do now is to associate all the latent variables that belong to that are associated with the ancestor. I want to add them in the ancestor class. So it's going to be a little bit cumbersome, but let me go through this. So first, I am hiding all classes except ancestors. So I have all the nodes that belong to the ancestor class. Then I'm selecting all nodes, and I make a right click on one of these nodes. I bring back all the other nodes and select the ancestors of my selected node. So as you can see, I have 42 nodes. So these that are selected. So these are the ancestors. And I'm choosing the ancestors of these nodes. So which means that since we have these little naive networks, I'm selecting the parent of these networks, subnetworks, right? So this way now I have 9 nodes that are selected. These are my nine factors, and I'm associating them with the class ancestors, right? So this is done for ancestors. Now I click on all to uncheck everything and check ancestor. So I can see that everything has been correctly associated. And then I'm going to select all these nodes, right? So now I have manifest and latent that correspond to the ancestors. I'm selecting all the classes and I'm going to invert the selection. So this way, I'm sure I have all the descendants, right? And now I have my 82 nodes. So 69 plus my latent variable. And I'm going to associate them with the class descendant. Now we have all our nodes that are associated with the correct classes. So we are good. And now I can just use, again, machine learning for creating my hierarchical semantic networks. So I'm first removing all the factors here that are not useful anymore. And then I'm going to rename the latent variable with the file I have exported a few minutes ago, and create here my constraint just to have, again, same thing, two different networks, right? So I'm forbidding here the relationship between different classes. And I'm using here taboo search for being able to keep the link between the manifest and the latent. So I just check delete and fix org. And now I have my hierarchical semantic networks, radial, symmetric layout, and now let's have a look at the 3D mapping, right? So just to really illustrate that, we have a hierarchical Bayesian network. So you see two levels. So the upper level corresponds to the latent variable, to the concept, and the lower level to the manifest variable, right? And if we go here, I'm going to just focus on the latent. So I'm setting a cost. I'm setting the manifest variable as not observable. So this way I can just analyze the relationship between the factors. And then I go to the 2D mapping just to analyze these factors, right? So this is now the view of the hierarchical, the upper level of the hierarchical semantic, right? So on the left, you have the ancestors. On the right, you have the descendant. So this is a way to get the sense of the dimensions are important in this domain, right? So now let's switch to causal networks, right? So I'm going to show you three different causal networks. So the first one is going to be the simplest version. Then we are going to have on the right the larger one, and we are going to conclude with the one at the bottom, right? So the first two ones are built with the causal network generator, and the last one with the causal relationship file. So here, let's start with what I call the simplest version. And so this is a network we are going to create automatically with Hellixia causal network generator. Still, we use the same target node delays, now, so in December, it was possible to use more than one node for this type of query. Now it's just a single node because it's the prompt is really too complex. We just use one node, delays here in schedule flight departure. We go to Hellixia, then causal network generator. We choose the completion model. Then the general context is the same. We use a node name. The language is English here. And here, same thing. We can choose a description length from short to long, or we just uncheck and then we let Hellixia to choose the optimal length. And you can also define here what is the complexity, what is the size of the network you want to have at the end of the day. So if you uncheck, same thing, you're going to let Hellixia define the size for you. But here, let's suppose that I want to have a simple network, right? And I can here check or not consequential variables, so that allows me to have the effects too, right? So here I'm going to have causes and effects that are connected with the delays. I can create classes and also structural priors, right? So this is something we added since December. So we can have automatically structural priors at the end of this work. So this is time consuming. So at least 1 or 2 minutes for that. So here we go quickly. And then we have this network after 1 or 2 minutes. And I'm going to format this causal network. So first thing, we go to the genetic grid layout and choose the bottom-up version, right? So we have this network here. And so a little bit of stretch. And let's analyze a little bit what are the variables that have been chosen here. So we have the flight scheduling, that is a direct cause of delays in scheduled flight. We have the external factors that are defined by weather condition and air traffic congestion. We have the aircraft technical issues that can be fixed with preventive maintenance, or at least we can reduce the priority to have these technical issues with preventive maintenance. We have also the operational efficiency that can be improved with the crew availability. And then we have three effects here: the cost, operational cost, passenger satisfaction, and the reputation of the airlines, right? So it's a simple network, but it makes sense, right? And as you can see, you have color. So this is something we did not have in December, because now we are able to estimate what we can qualify as causal effects, negative and positive causal effects, right? So when it's red, it has a negative impact, obviously, and blue, positive. So now we are going to create classes here just to have the depth of the node in the network. So I'm going to click on the screamer here and then choose generate classes. And we have just one option here, depth. I'm choosing depth. So this automatically create 4 classes, 1 class per depth in the network. And I'm associating 1 color per depth, and it's a random color. So this way we have, so in pink, we have the root nodes, if you will. I'm choosing the badges here. And as you can see, we have these nice badges here, which you can always do that. But now we have changed a little bit the workflow for that. It's super convenient now. So let's have a look at the rendering properties. We just make a right click on the node and select properties, rendering property, edit all. And as you can see, we have, so in this setting, we have a fixed width of the badge, which is 250. We are using the node name. And we have this new option, which is here, colors link. So this is just to have the same color everywhere. So we are using the node color that is defined with the class, as I did just a few minutes ago. And it automatically used also for the background of the node. So this way, if I change the color with another tool, it's going to be automatically updated in my badges, right? So this is very convenient. And when it's dark, so the font will be in white. And when it's light, it's going to be in black automatically. And here what I did, I chose a bigger font and it's center, right? So this allows me to have these nice badges. And since we have what I call a fully specified network, because we have also the probabilities, we can also use monitors here. So I'm going to define them as monitors. And as you can see, I have the same rendering here. So I have the nice name here. And I'm going to set delay as a target node, switch to validation, and then now play a little bit with this network. But let's focus on the causal relationship first. And so by displaying the comment here, that we have a description of the causal relationship. So we have not only the description of the causal relationship, but we have also a coefficient that is between -100 and 100. And this corresponds to an estimation of the causal effect. So obviously, it's just, you don't have to trust this coefficient really, but it gives you an idea, right? So it's just a way to weight the relationship. So again, in red, this is negative, in blue, positive. So in this network, we can see that the preventive maintenance has a negative impact, so can reduce the aircraft technical issues. And here, the causal effect is estimated to -80, right? But we have a connection between air traffic congestion to external factors, and the contribution of this air traffic congestion is 50, right? Same weight for weather condition, right? So here, you can see also this new feature. You can now move the comment of the arc. Before they were just center, but since we are using more and more this comment, before we had just coefficient, now we have text associated with these links. So we can now change the location of these comments, right? We just have to find our automatic layout algorithm for this comment. And I'm gonna now switch to see the structural priors. So because I check the option, so I have all these priors that have been created. The weight of the prior, before it was 1. Now we are using the absolute value of the causal effect. So it's quite convenient then for if we have to later machine learn a network. Okay. Then, so I'm clicking on this icon just to show the information that are associated with the icon. And if I hover over the icon that represents a function, I can see that I have formulas that are associated with my node. And here you see I have a dual noisy OR. So this is a new formula that we have created a few days ago just to be able to capture positive and negative effects. Since we have this efficient between -100 and 100, we have created this formula to be able to define a kind of noisy OR that works in both ways, positive and negative, right? So this way we have automatically conditional probability tables that are populated. Right, same thing for this one. So all these nodes, each time you see a little f, this means that we have a formula that is associated. Right? So now if we have a look at the conditional probability table, we have this port that has been created with a dual noisy OR. So first row, when everything is false, you see it's 99.1 because we have defined a leak. Even though we have all these causes that are not true, we still have 1% of risk to have a delay for all the causes that have not been represented in this network. And then we have these different probabilities. And this is the formula. And finally, we are going to use DALI 3 for creating a nice icon, right? DALI 2 is not really good, but DALI 3 is really impressive. So we just use here the node comments instead of just the node name. So this allows to have more content. And then, so you can see we are going to zoom in these icons, but it's quite impressive. This one, for example, the true availability, it's very politically correct, as you can see. We have almost the same number of men and women, and we have all the colors, even blue guys, right? So it's quite impressive. And then we have, so sometimes lots of details, but it's quite nice. So if we look at this one, air traffic congestion, lots of planes, delay, satisfaction. And now we're going to just go through inference just to go through one or two scenarios. So let's suppose that we have a true availability that is true, right? So this will increase probability that we have operational efficiencies that has them decrease or negative impact on the delay, so that we are improving the problem here. Then if we do say that we have also preventive maintenance, this is decreasing the probability to have problem with the aircraft. And then this is also decreasing probability to have delay. And then if we just use soft evidence here or hard here, that's what I use. So we have this density of aircraft in the airspace. So we have, given that we have two factors that have a weight of 50, then we are sure that we have external factors problem. And then flight scheduling, which is here true. And at the very end, we have this 87% of risk to have delays. And we have the impact on the effects, right? We can clear all and then do the same thing the other way around. So setting evidence on the symptoms or the effects and see what is the impact on the different causes, on the ancestors, right? Even though, again, this is something that you have to double check with your expert knowledge, right? Because this is really the defined automatically. So now let's go through a larger network. So this is the network we are going to create. And for that, so I'm creating the node still, delays in scheduled flight departure. I go to Hellixia, then the causal network generator. And here I'm going to set a high complexity. So I'm still using the same settings otherwise, but here I'm going to set high for complexity. I'm also selecting consequential variable, right? Have to wait 1 or 2 minutes. And then we have this large network. We use a genetic grid layout. And we have all these nodes, right? So we can have a look. We are going to render first this node with badges to have also access to the comments. And then if we analyze a little bit what is there, so we have shooting delays, security issues. We have a block corresponding to operational efficiency that is defined by 5 variables. We have the regulatory compliance, staff training, operational communication, ground staff efficiency, resource allocation. This has a negative impact on the delay, so which means that it is reducing the priority to have delays. We have the aircraft turnaround time, air traffic control restriction, and all these notes. I'm not going to spend more time on that. But then the thing is, here, for example, we see that we have fueling delays that is directly connected to delays in the schedule flight. But perhaps, I think it can make sense, but it's instead of being directly connected to delays, being connected to the aircraft turnaround time, right? So let's suppose that we have this doubt or we have this expert knowledge. So let's say that, okay, so I want to check if this is true. So I'm going to just move to fueling delays on top of around turnaround time. I'm going to select these 2 nodes, fueling delay and turnaround, and go to the pairwise causal link. So this is just testing if we have a causal relationship between these 2 nodes. So we are going to use a dot comment so it's really trying to find if there is a causal relationship between delays in aircraft refueling process and time taken for aircraft to be ready for next flight. Description length, same thing. And I can also create a structural prior. So this is a new option too, right? So we are analyzing this pairwise relationship, and indeed, Hellixia finds that there is a link between these 2, and this is from fueling to aircraft turnaround. And the causal effect is estimated to 75. So here, as you can see, I double click on the link. So this is also a new feature. We have now an arc editor. So double clicking on the link allows you to directly edit the command that is associated with the link. You can also change the properties and the rendering properties. So here, I can change the color, I can change the size of the link and so on, right? And now I have also, since I've used this causal pairwise relationship, I have also updated automatically as a formula. And again, it's based on the door noise error. So we have these formulas that have been automatically created. And since I have these new links that have been connected, my structural prior have been also updated, and I have this new prior here, right? So now that I have this link, I can get rid of the direct connection between fueling delays and delay in scheduled flight. So I'm going to delete this link. And I need then obviously to update the formula, right? So I go to formula and I'm going to get rid of the part that correspond to fueling delays. So now I have this causal graph that have been a little bit modified, and using the genetic grid layout, updating the representation of this causal network. And now let's suppose that I'm curious. So curious in the sense by using the definition of Thomas Hobbes, which means that this is a knob of the knowledge of the causes. So I want to know the causes of the causes. So here, let's suppose that I want just to investigate what are the potential causes for fueling delays. Okay. So I'm going to do the same using use the same process here and select fueling delays, and then go to Hellixia and use network, the causal network generator. But now just using the name, and here reduce the complexity and remove the consequential variable, because I don't want to find what are the effects of fueling delays. I already have them. I just want to have the causes, and I want to have a very small network. So now we have new nodes. And so we have one class per causal network. So I have one causal network that was generated for delay, and I have one for fueling delays. So I'm selecting these two classes. I'm going to associate random colors with this class. And then we have this representation. So just again, genetic grid layout. And now if we see, so in black, we have the new nodes. So we have that weather condition has an impact on the fueling infrastructure. We have this one communication system that has also an impact on the operational efficiency. We have the fuel truck availability that have an impact on fueling delays, the fueling infrastructure. So we have also obviously the causal effects. And so again, all the black nodes are the new ones, even though we have connection between red and blacks, right? So everything has been merged, if you will. And so here, let's go to the new nodes. And we can see that this one, good communication, enhance efficiency. So the communication system here has an impact on the operational efficiency, but it should be positive, because you see the link is in red, but the comment looks like it should be the other way around, because it's like it's a good communication and enhance efficiency. So this is where it's a good illustration of the trust you can have. So you have always to double check. Here, obviously, this is reverse. So we're going to have to edit this link. So first, we're going to just change the comment and set +60 instead of minus, and change the color. Put it in blue. Then we go through the other one. So we can see that this one, same thing. So it improved. So it's reversed too. Blue. And the last one, stuffing levels, same thing. Also the opposite. So it just mixed the coefficient here. And obviously we need also to update the formulas now to reverse the sign and set this connection positive. Right? Now we have a network that makes more sense. So it's more complex. But again, what I wanted to show was that you have to double check. So don't make a 100% trust what is created. It's just an assistant. You have to double check with your expert knowledge if it makes sense or not. Right? And so the last topic, or the last feature I wanted to show you today, is the causal relationship finders that allows to also to create causal Bayesian network, but by using a set of nodes instead of starting from scratch, if you will. So this is a network we're going to create here. And so same thing, I'm creating my target node. Then I'm going to use the dimension elicitor here. And here just use two keywords, because I want to create a very simple one. So I'm going to choose causes and effect and just select 5. So I want the top 5 causes, top 5 effects. Then I'm using GPT-4, no knowledge file, just node name, description length, and so on, and hit submit as usual. Then a few seconds later, I have this result. So I have 10 nodes, no duplicates, right? So I have the passenger discontent, misconnection. So these are the effects. And for the causes, we have again weather condition, air traffic control, and so on. So now that I have these 10 nodes, I'm going to find the relationship between these 11 nodes, because I have these 10 plus 1. So what I was before, I would have to use this pairwise causal links, which means testing all pairs of nodes to see if there is a causal impact. So it would be cumbersome. So instead, now you can use a causal relationship finder. So you select all nodes or you don't select anything. And then you are going to have here on the top the list of the nodes that are going to be used for creating this causal Bayesian network. We choose node name, node long name or node comments, description length, and the classes. So you have this option, even though I'm not using it in this example, to create latent variables. So here I'm going to just create a causal graph based on these 11 nodes, but I can also, for some example, it's worthwhile to also try to add some latent variables that can simplify the network. So to create factors, if you will. So same thing, it's quite long. And then we have this causal networks. Let's format it. Genetic grid layout. And we have this bow representation. Monitors. And we have these comments. So the weather impact is estimated to 50. Same thing for crew, for ATC. So just boarding, security delays due to during boarding, that is estimated to 30. And that we have the effect. And now I'm going to switch to validation and use the report, that analyze the connections. So the relationship report. So just using the Kullback library divergence to estimate the strength of this connection, and use the Hellixia report analyzer to create a report, a text report based on these numbers, right? So I have to define the context. So my context is a flight operation coordination. And then here it's also new. I can change the language. So it was in French before, but I'm going to go back to English and choose the complexity of the report. I choose here high complexity. And then you have this report that is generated that describe your network, right? So based on the strength of the relationship, so the strength of the relationship and the strength of the node. And then here, so you have the description of the domain. It can be very convenient, right? So this was all the new feature I wanted to show you today. Oops. Here, just before concluding, on the website, on the Hellixia website, you have first the documentation, but you have also lots of examples, mainly semantic networks, but now we are starting to add the causal networks too. And you have, for example, these ones that I added last week with the atopic dermatitis, which is more or less the same workflow as what I used here. So you have a step-by-step description of this generation of causal Bayesian network for describing atopic dermatitis. And after that, I want to thank you for your attention.
Thank you, Lionel, for an absolutely fascinating presentation. It's really exciting to see how large language models can be leveraged for discovering causal relationships. So let me conclude our event with a quick outlook on our next major event this year. So on April 11th and 12th this year, we will be hosting our semi-annual BayesiaLab conference in Cincinnati, Ohio. And for the first time since the beginning of the pandemic, our community will meet again in person. I think this will be a great opportunity to learn from practitioners about practical applications of BayesiaLab and, of course, Bayesian, and of course, Hellixia. In the context of the conference, Lionel will also teach the highly acclaimed introductory and advanced BayesiaLab courses. The conference and the courses are open for registration, So please start making travel plans for your trip to Cincinnati. All right. This concludes today's webinar. Thank you, Lionel, for a brilliant talk. And
You're
thank
welcome.
you all for participating in today's event. Have a wonderful day.